Somewhere beyond the faint glow of the stars you can see with your eyes, far past the familiar constellations that humans have named for thousands of years, there are worlds. Not imagined, not theoretical, but confirmed. Entire planets orbiting distant suns, moving in silence through deep space. These are not part of our solar system. They do not belong to our cosmic neighborhood. And yet, over the last few decades, we have begun to find them. Slowly at first, then in waves. Planets beyond our solar system. Exoplanets. Before we go any further, take a moment to settle in, wherever you are. Maybe you're lying in bed, maybe you're watching in the quiet of the night, or maybe you're just letting this play in the background. And if you enjoy exploring these kinds of mysteries, the kind that sits somewhere between established science and unanswered questions, consider subscribing to the channel. And I'm always curious, where in the world are you listening from right now? Because tonight we're going to take a careful, unhurried look at something that is both very real and still, in many ways, deeply unknown. The discovery of exoplanets is not ancient history. In fact, for most of human existence, we didn't know if planets even existed beyond our solar system. Philosophers debated it, scientists speculated about it, but there was no proof. It wasn't until 1992 that the first confirmed exoplanets were detected, orbiting a pulsar, an unusual and extreme type of star. That alone was strange. Not planets around a calm, sun-like star, but around the remnants of a dead one. Then, in 1995, everything changed. A planet was discovered orbiting a star much more like our own sun. That discovery opened the door. Since then, thousands more have been found. Not guessed, not imagined, measured, tracked, confirmed through data. The mainstream explanation for how we find these planets is grounded in careful observation. We don't usually see exoplanets directly because they are too distant and too dim compared to their stars. Instead, we detect them indirectly. One of the most common methods is called the transit method. When a planet passes in front of its star from our point of view, it causes a tiny dip in the star's brightness. That dip can be measured. Repeated dips at consistent intervals suggest a planet is orbiting that star. Another method involves measuring the wobble of a star. A planet's gravity pulls slightly on its star, causing it to shift ever so slightly. Sensitive instruments can detect that motion. Again, repeated patterns reveal the presence of an orbiting body. So, from a scientific standpoint, this is not guesswork. These detections are based on consistent, repeatable data. Patterns that match predictions, signals that align with orbital mechanics. And yet, this is where things begin to get interesting. Because while the methods are sound, what we're finding is not always what we expected. Many of the first exoplanets discovered were nothing like the planets in our own solar system. There were hot Jupiters, massive gas giants orbiting extremely close to their stars, completing an orbit in just a few days. That alone challenged existing models of planetary formation. According to traditional theories, large gas giants should form far from their stars, where temperatures are lower. So how did these massive planets end up so close? The mainstream explanation is planetary migration. The idea is that these planets formed farther out and then gradually moved inward over time due to gravitational interactions. It's a reasonable theory, supported by simulations, but it also raises questions. How stable are these systems? How common is this migration? And why do we see such a wide variety of planetary arrangements, many of which look nothing like our own solar system? Because when you start to look at the data as a whole, patterns begin to emerge, but so do inconsistencies. There are planets that orbit two stars at once, moving in complex, shifting paths. There are planets with densities so low they're described as cotton candy worlds, barely held together. There are planets so dense they defy easy classification. Some are tidally locked, with one side permanently facing their star, creating a world where half is in constant daylight and the other in eternal night. And then there are the so-called super-Earths, planets larger than Earth but smaller than Neptune. Interestingly, our solar system has none of these, not one. Yet they appear to be among the most common types of planets in the galaxy. So the question becomes, is our solar system typical, or is it the exception? From a mainstream perspective, the answer is still unclear. Our sample size is growing, but it's still limited. We're observing from a distance, interpreting signals, building models. Science is doing exactly what it's supposed to do, gathering data, refining theories, adjusting to new information. But from a more speculative angle, you might start to wonder whether the diversity we're seeing points to something deeper, not something supernatural or fantastical, but something we don't yet fully understand about how planetary systems form and evolve. Because if the standard model struggles to explain certain observations, that doesn't mean the model is wrong. It means it's incomplete. And this is where exoplanets become more than just distant worlds. They become clues. For example, consider the sheer number of planets that seem to exist in what scientists call the habitable zone, the region around a star where conditions might allow liquid water to exist. This doesn't mean these planets are habitable. It simply means they are in the right range of distance from their star. But even defining a habitable zone is more complicated than it sounds. It depends on the type of star, the planet's atmosphere, its composition, its rotation, its magnetic field, dozens of variables. And yet, we often simplify it into a single range, a neat band where life could exist. That simplification is useful, but it might also be limiting. Because what if life doesn't require the same conditions we do? What if the definition of habitability is broader than we currently assume? These are not wild claims. They are open questions, and they highlight something important. The more we discover, the more we realize how much we don't know. There's also the question of detection bias. The methods we use are more likely to find certain types of planets, large ones, close to their stars. That means our current catalogue of exoplanets may not represent the true distribution of planets in the galaxy. It's shaped by what we can detect, not necessarily by what is most common. So when we see patterns, we have to ask, are these real patterns, or are they artifacts of our methods? Again, this doesn't undermine the science. It just reminds us to be careful in our interpretations. And perhaps that's the most interesting part of all this. Exoplanets sit at the intersection of what we can measure and what we are still trying to understand. They are real, physical objects, confirmed by data. But they also represent the limits of our current knowledge. Each new discovery adds a piece to the puzzle. But it also reveals how large the puzzle really is. And as you let your mind drift through this idea, through the quiet realization that there are thousands of worlds out there, each with its own conditions, its own history, its own unknowns, you begin to see the bigger picture. We are not just discovering planets. We are expanding the boundaries of what we consider possible, but we're doing it slowly, carefully, one observation at a time. Because in science, especially when dealing with something this vast, it's not about jumping to conclusions. It's about asking better questions. And exoplanets might be some of the best questions we've ever found. As the catalogue of exoplanets began to grow, something subtle but important started to shift in the way scientists thought about the universe. At first, each discovery was treated almost like an exception, something unusual to be explained within the existing framework. But over time, as the number climbed from a handful to dozens, to hundreds, and then into the thousands, the pattern became harder to ignore. It wasn't that these strange worlds were rare. It was that our expectations had been too narrow. What we once thought of as a normal planetary system, something resembling our own, with small rocky planets near the star and gas giants farther out, started to look less like a rule and more like just one possibility among many. And this realization didn't come from speculation. It came from missions like Kepler's Space Telescope, which spent years staring at a single patch of sky, monitoring over 150,000 stars continuously, waiting for the slightest dimming that might indicate a planet passing in front of its star. The patience of that approach is almost difficult to comprehend. Years of watching, measuring tiny fluctuations in light, building up data sets so precise that even the smallest periodic change could be identified. From that data, something remarkable emerged. Not just individual planets, but entire systems, some with multiple planets orbiting in tight, compact arrangements, far closer to their stars than anything we see in our solar system. In some cases, several planets orbit within a distance smaller than Mercury's orbit around our Sun. From a mainstream perspective, these systems can be explained through variations in how protoplanetary disks evolve, the clouds of gas and dust that form around young stars. Differences in temperature, density, and angular momentum could lead to very different outcomes. Slight changes early on could cascade into dramatically different planetary architectures. And yet, even within that explanation, there are details that don't always fit neatly. Because when you look at these tightly packed systems, many of them appear to be surprisingly stable. Their orbits are often in resonance, meaning the planets exert regular, repeating gravitational influences on each other that keep the system balanced over long periods of time. It's almost like a kind of natural tuning, a gravitational harmony. But how does such precise stability emerge from what is supposed to be a chaotic formation process? The standard answer is that over time, unstable configurations simply don't last. They collapse, collide, or eject planets from the system, leaving behind only the stable arrangements we observe. In other words, what we're seeing is the result of natural selection on a cosmic scale. Only the stable systems survive long enough to be observed. That makes sense, but it also raises a quiet, lingering question. How many unstable systems existed before reaching that point? And what did they look like during those early stages? Because we are only seeing snapshots, moments frozen in time, often billions of years after these systems formed. We are not watching them evolve in real time. We are reconstructing their histories based on what remains. And reconstruction, by its nature, involves interpretation. There's another layer to this that becomes more apparent the deeper you go into the data. The stars themselves vary widely in type, size, temperature, and lifespan. Some burn hot and fast, living only millions of years. Others burn slowly, lasting tens or even hundreds of billions of years. And the planets around them must exist within those constraints. For example, red dwarf stars, which are smaller and cooler than our Sun, are the most common type of star in the galaxy. Many exoplanets have been found orbiting these stars, often within very close distances, because that's where the habitable zone would be for a cooler star. But red dwarfs are also known for intense stellar activity, flares and radiation bursts that could strip away planetary atmospheres over time. So while a planet might technically sit within the habitable zone, the environment could be far more hostile than that term suggests. Again, this doesn't contradict the science. It adds nuance to it, because the idea of habitability becomes less of a simple category and more of a spectrum. A planet might have some conditions favorable to life and others that are not. It might be habitable in theory, but not in practice, or habitable for forms of life very different from what we understand. And this is where the conversation begins to shift from detection to interpretation. Because detecting a planet is one thing, understanding it is another entirely. Take atmospheric analysis, for example. In recent years, instruments have become sensitive enough to analyze the light passing through a planet's atmosphere as it transits its star. By studying the absorption lines in that light, scientists can infer the presence of certain gases: water vapor, carbon dioxide, methane. This is often presented as a major step toward finding signs of life, and it is. But it's also more complicated than it appears, because many of these gases can be produced by non-biological processes. Methane, for instance, can come from geological activity as well as biological sources. Oxygen, which we often associate with life, can accumulate through purely chemical reactions under certain conditions. So when we detect these gases, we're not detecting life. We're detecting possibilities. And the interpretation of those possibilities depends on context. The combination of gases, the temperature, the pressure, the radiation environment, all of these factors must be considered together. It's a bit like trying to understand a distant world through a thin veil of light, filtered across unimaginable distances. The data is real, but it is also incomplete. And that incompleteness leaves room, not for wild conclusions, but for careful curiosity. Because if there's one consistent theme in the study of exoplanets, it's that each answer tends to reveal more questions. Why do some planets form in tightly packed systems while others are widely spaced? Why do some migrate inward while others remain distant? Why does our solar system lack certain types of planets that seem common elsewhere? From a scientific perspective, these are active areas of research. Models are being refined, simulations are being run, new missions are being planned. But from a broader perspective, it's hard not to notice that the universe appears far more varied, far more flexible in its outcomes than we once assumed. And that realization has a quiet kind of weight to it, because it suggests that the processes that shape planetary systems are not rigid. They are dynamic, sensitive, and perhaps influenced by factors we don't yet fully understand. Not unknown forces, not hidden agendas, just complexity. The kind of complexity that only becomes visible when you start to gather enough data to see beyond your initial assumptions. And as you continue to drift through this idea, letting your mind follow the patterns and the questions without needing immediate answers, you begin to see exoplanets not just as distant objects, but as part of a much larger story. A story about how systems form, how they evolve, and how much variation can exist within the same basic rules of physics. It's a reminder that even with all our technology, all our measurements, all our models, we are still at the very beginning of understanding what's out there. And maybe that's what makes this so compelling. Not that we've found thousands of new worlds, but that each one challenges us, in small and subtle ways, to rethink what we thought we already knew. As more powerful instruments came online, and the data became more precise, attention began to shift toward a smaller, more intriguing subset of exoplanets, the ones that, at least on the surface, seem somewhat familiar. Not gas giants skimming the edges of their stars, not extreme worlds with impossible densities, but rocky planets, solid, Earth-sized or slightly larger, existing at distances where temperatures might allow liquid water to remain stable. These planets began to draw attention not because they were proven to be habitable, but because they represented something closer to a comparison point. A reference, a way to ask a very specific question: how similar can another world be to Earth, and still be fundamentally different? One of the most discussed examples is Proxima Centauri b, a planet orbiting the closest star to our solar system, Proxima Centauri. From a distance of just over 4 light-years, it exists practically next door in cosmic terms. Its size suggests it could be rocky. Its orbit places it within the star's habitable zone. On paper, it checks several boxes. From a mainstream scientific standpoint, Proxima Centauri b is one of the most promising candidates for further study. But even here, the details complicate the picture. Proxima Centauri is a red dwarf star, known for frequent and intense stellar flares. These bursts of radiation could have a significant impact on the planet's atmosphere, potentially stripping it away over time or altering its chemical composition. So while the planet sits in the habitable zone, the actual conditions on its surface could be far from stable. It might have an atmosphere, or it might not. It might retain heat effectively, or experience extreme temperature swings. It might even be tidally locked, with one side permanently facing the star, creating a sharp divide between light and darkness. And this is where the pattern begins to repeat. The closer we look, the more variables emerge. Another often discussed world is TRAPPIST-1e, part of the TRAPPIST-1 system, a system containing 7 Earth-sized planets orbiting a single ultra-cool dwarf star. Several of these planets fall within what we define as the habitable zone. From a structural perspective, the TRAPPIST-1 system is fascinating. The planets are packed closely together, with orbital periods measured in days rather than months or years. And yet, they exist in a delicate gravitational balance, their orbits locked into resonant patterns that keep the system stable. Mainstream models suggest that such systems can form through migration and interaction within the protoplanetary disk, eventually settling into these resonant configurations. But again, the precision of that arrangement raises questions, not contradictions, but points of curiosity. Because when you see multiple planets moving in near-perfect synchronization, it invites a deeper look into the processes that could produce such order from initial chaos. And then there's the matter of composition. Some exoplanets appear to have densities consistent with rocky worlds, like Earth. Others fall somewhere in between, suggesting thick atmospheres or layers of volatile materials. There are even planets that may be water worlds, with vast global oceans potentially hundreds of kilometers deep, lacking continents entirely. From a scientific perspective, these variations can be explained through differences in formation conditions, where in the disk the planet formed, how much material it accumulated, how it interacted with other bodies. But the sheer diversity continues to expand the range of what we consider possible. And with that expansion comes another subtle shift. Because as the definition of an Earth-like planet becomes less rigid, the question itself begins to change. It's no longer just about finding a planet that looks like Earth. It's about understanding how many different paths could lead to something that supports complex chemistry, or even life. And here, the conversation becomes particularly careful, because while it's tempting to associate certain conditions with the presence of life, science remains cautious. The existence of liquid water, for example, is often treated as a key indicator, and for good reason. It's essential for life as we know it. But as we know it is an important qualifier. We are working from a sample size of 1. Earth is the only planet where life has been confirmed. Every assumption we make about habitability is based on that single example. And while it provides a valuable framework, it may not represent the full range of possibilities. So when we look at planets like Proxima Centauri b or TRAPPIST-1e, we are not identifying life. We are identifying conditions that might, under certain circumstances, allow for it. And even then, those circumstances are complex. Atmospheric composition, magnetic fields, geological activity, orbital stability. Each of these factors plays a role. Remove one, and the system changes. Adjust another, and the outcome shifts. It's less like checking boxes, and more like balancing variables. And this balance is not always easy to interpret from a distance. Because all of our observations, no matter how precise, are still indirect. We are analyzing light curves, spectral lines, gravitational effects. We are building models that fit the data. But we are not there. We are not sampling the atmosphere directly. We are not observing the surface in detail. We are, in a sense, reconstructing entire worlds from shadows and signals. And that process, while incredibly powerful, has its limits. It leaves room for uncertainty, not the kind that undermines the science, but the kind that reminds us to remain open to revision. Because history has shown that as our tools improve, our understanding evolves. What seems clear today may become more nuanced tomorrow. And this is where a more speculative line of thought begins to emerge, not as a conclusion, but as a question. If planetary systems can form in so many different configurations, if planets can exist in such a wide range of environments, if the ingredients for complex chemistry appear to be relatively common, then how rare or how common is something like Earth? From a mainstream perspective, this is still an open question. Estimates vary widely. Some suggest that Earth-like planets could be abundant in the galaxy. Others point out that the specific combination of conditions that make Earth stable over long timescales might be less common. And both perspectives are grounded in data, interpreted through different models. But from a broader point of view, there's something quietly profound about the fact that we can even ask this question now. Just a few decades ago, we didn't know if any planets existed beyond our solar system. Now, we are comparing worlds across light years of distance, analyzing their atmospheres, estimating their compositions, mapping their orbits. We've moved from wondering if planets exist to wondering what they're like. And that shift changes everything, because it transforms the universe from something distant and abstract into something populated, dynamic, varied, not just stars scattered across the darkness, but systems, structures, worlds. And as you let that idea settle in, as you imagine these distant planets orbiting their stars in quiet, repeating cycles, each one with its own conditions, its own unknowns, you begin to feel the scale of it, not in a dramatic or overwhelming way, but in a slow, steady realization that the night sky is not empty. It's filled with places we can't yet visit, places we can barely observe, but places that are there nonetheless. And perhaps the most interesting part is not what we've already found, but what we haven't yet detected. Because if our current methods are limited, if our observations are shaped by what we're able to measure, then there may be entire categories of planets that we haven't even begun to see, not hidden in a mysterious sense, just beyond the reach of our current tools. And that possibility, quiet and understated, sits at the edge of everything we've discussed so far. A reminder that discovery is not a finished process, it's ongoing, and in many ways, just beginning. As the search continued and detection methods improved, scientists began to notice something that, at first glance, seemed almost counterintuitive. The universe does not necessarily favor simplicity. Instead of neat, predictable systems, what kept appearing in the data were environments shaped by extremes, by interactions, by long histories of movement and change that left behind systems far more dynamic than anyone initially expected. And one of the clearest examples of this comes from a class of exoplanets that for a long time didn't even fit comfortably into existing categories. These are the so-called super-Earths and mini-Neptunes, planets that fall between Earth and Neptune in size and mass. They are not quite like our planet, and not quite like the gas giants we're familiar with. They occupy a kind of middle ground that, interestingly, does not exist anywhere in our own solar system. From a mainstream perspective, this is not a contradiction, but it is a point of curiosity. Models of planetary formation allow for these types of planets to form, depending on how much material is available in the protoplanetary disk and how quickly a forming planet can accumulate gas before the disk dissipates. In some systems, a planet might grow large enough to capture a thick atmosphere, becoming more like a mini-Neptune. In others, it might remain predominantly rocky, forming what we call a super-Earth. But the line between these categories is not always clear. Some planets appear to blur that boundary, showing characteristics of both. Their densities suggest a mixture of rock, water, and gas. Their atmospheres may be thick or thin, depending on factors that are still being studied. And because we are observing these worlds from such great distances, much of what we infer comes from models that must account for multiple possibilities. So even within this classification, there is uncertainty. And that uncertainty becomes more noticeable when we look at how common these planets appear to be. Super-Earths and mini-Neptunes are among the most frequently detected types of exoplanets. In fact, they may represent one of the dominant forms of planet in our galaxy, which leads to a simple but intriguing question. If these types of planets are so common, why don't we have any in our own solar system? From a scientific standpoint, there are several possible explanations. It could be related to the timing of planet formation, the distribution of material in the early solar nebula, or the gravitational influence of larger bodies like Jupiter and Saturn, which may have shaped the development of the inner solar system in ways that prevented intermediate-sized planets from forming. This is sometimes referred to as a kind of architectural difference. Our solar system may simply be one configuration among many, shaped by a specific set of initial conditions that led to the arrangement we observe today. And yet, even within that explanation, there's a quiet implication. If our solar system lacks one of the most common types of planets, then it may not be a typical system. Not rare in a dramatic sense, but not necessarily representative. And that idea becomes even more interesting when we consider how much of our understanding of planetary science has historically been based on a single example, our own system. For a long time, it was the only reference point we had, the only model. Now, with thousands of exoplanets observed, that model is being expanded, adjusted, and in some cases, challenged. But the process is gradual, because each new discovery adds complexity, and complexity takes time to understand. There are also planets that push the boundaries of what we consider physically plausible, at least at first glance. Worlds like Kepler-36b and Kepler-36c, which orbit the same star at very similar distances, yet have dramatically different densities, one dense and rocky, the other much less dense, with a thick gaseous envelope. From a straightforward perspective, this can be explained by differences in formation history and atmospheric loss. Perhaps one planet retained its atmosphere, while the other lost it due to stellar radiation. Perhaps they formed at different distances and migrated inward, ending up in close proximity. But when you step back and look at the system as a whole, it presents a scenario that is unusual. Two planets, side by side in cosmic terms, with fundamentally different compositions. It's not that this is impossible, it's that it requires a sequence of events that, while plausible, is not immediately obvious. And this pattern of plausible but complex explanations appears again and again in exoplanet data. Another example comes from planets with extremely eccentric orbits, where the distance from their star varies dramatically over the course of a single orbit. These planets might experience intense heating as they approach their star, followed by rapid cooling as they move away. The environmental conditions would be in constant flux. From a mainstream standpoint, such orbits can result from gravitational interactions, either with other planets or nearby stars. Over time, these interactions can stretch and distort orbits, creating the elongated paths we observe. But again, this points to systems that are not static. They are shaped by interactions, by movement, by change. And this brings us to a broader realization. Planetary systems are not just formed, they evolve. They shift over time, sometimes dramatically. Planets can migrate inward or outward. They can be ejected from their systems entirely. They can collide, merge, or break apart. The arrangement we observe at any given moment is the result of a long and complex history. And that history is not always easy to reconstruct, because we are seeing the end result, not the process. We are looking at systems that have already settled, at least temporarily, into stable configurations. But the path they took to get there is often hidden, inferred only through models and simulations. And while those models are grounded in physics, they are also sensitive to initial conditions. Small differences early on can lead to very different outcomes later. This sensitivity introduces another layer of uncertainty. Not uncertainty in whether these planets exist, they clearly do, but in how exactly they came to be the way they are. And this is where a more reflective line of thought begins to take shape. Because if planetary systems can vary so widely, if their histories can diverge based on subtle differences, then the universe may be less predictable in terms of outcomes than we once assumed. Not chaotic in a random sense, but open-ended, capable of producing a wide range of structures from the same underlying laws. And that idea carries a certain weight, because it suggests that the conditions we observe, whether in our own solar system or elsewhere, are not inevitable. They are the result of specific sequences of events shaped by timing, interaction, and environment. And if that's the case, then each planetary system is, in a sense, a record of how those factors came together over time. Some systems may be relatively simple, others highly complex. Some may resemble each other, others may be entirely unique. But all of them are part of the same larger framework, the same physical laws, the same processes, just expressed in different ways. And as you let that idea settle, as you imagine these distant systems evolving over millions or billions of years, shifting and stabilizing, forming and reforming, you begin to see exoplanets not just as isolated discoveries, but as pieces of a much larger pattern. A pattern that we are only beginning to recognize. Not fully mapped, not fully understood, but slowly, steadily, becoming clearer. And perhaps the most interesting part is that this clarity doesn't come from finding simple answers. It comes from learning how to ask better questions. Questions that account for complexity. Questions that remain open to revision. Questions that follow the data, even when it leads somewhere unexpected. Because in the study of exoplanets, expectation has often been the thing that needed to change, not the universe. And that quiet shift, from assuming we know what to expect, to recognizing how much variation is possible, may be one of the most important discoveries of all. As the number of confirmed exoplanets continued to rise, and as patterns slowly began to emerge from what once looked like scattered, unrelated discoveries, attention started to shift towards something even more subtle. Not just the planets themselves, but the methods we use to find them, and how those methods might quietly shape what we think we're seeing. Because every detection technique, no matter how precise, has its own limitations. And those limitations don't just restrict what we can observe, they influence the overall picture we build. Take the transit method again, the one responsible for discovering thousands of exoplanets, especially through missions like Kepler Space Telescope. It relies on a very specific alignment. The planet must pass directly between its star and our line of sight. If that alignment doesn't occur, the planet remains invisible to this method, no matter how large or close it might be. From a statistical standpoint, this means we are only seeing a fraction of the planets that actually exist. Systems that are tilted even slightly out of alignment relative to Earth may go completely undetected. So when we look at the thousands of planets discovered through transits, we have to remember they represent a filtered sample, a sample shaped by geometry. And then there's the radial velocity method, which detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. This method is more sensitive to larger planets, especially those close to their stars, because they exert a stronger gravitational influence. So again, the data we gather is not a perfectly balanced representation. It leans towards certain types of planets, massive ones, close in orbits, systems where the signal is easier to detect. From a mainstream scientific perspective, this is well understood. Researchers actively account for these biases when analyzing the data. Statistical models are used to estimate how many planets might exist beyond what we can directly detect. But even with those corrections, there is an inherent limitation, because you can only adjust for what you know. And that leaves open a quiet possibility that there may be categories of planets or entire types of systems that are currently underrepresented in our observations simply because they don't produce signals that our instruments are optimized to detect. Not hidden in any deliberate sense, just subtle. For example, planets that are very far from their stars, with long orbital periods, are much harder to detect using current methods. A planet that takes hundreds of years to complete one orbit would require generations of observation to confirm through traditional techniques. Similarly, smaller, Earth-sized planets in wider orbits produce weaker signals. Their transits are less frequent, their gravitational effects more difficult to measure. So while we have discovered thousands of exoplanets, it's entirely possible that we are only seeing the most detectable fraction of a much larger population. And that idea becomes even more interesting when you consider how quickly our detection capabilities have improved. In just a few decades, we've gone from detecting the first exoplanets to analyzing the atmospheres of some of them. Instruments have become more sensitive, data analysis techniques more refined, observations more precise. Missions like James Webb Space Telescope are now capable of examining the chemical signatures of distant planetary atmospheres with a level of detail that would have seemed almost impossible not long ago. From a mainstream perspective, this represents a natural progression of technological advancement. Better tools lead to better data, which leads to deeper understanding. But it also introduces a shifting baseline, because as our tools improve, the universe we observe changes with them. Not in reality, of course, but in our perception of it. What was once invisible becomes visible. What was once undetectable becomes measurable. And with each improvement, the picture becomes more detailed, but also more complex. This is something that often goes unnoticed. The idea that our understanding of the universe is not static, but evolving alongside our ability to observe it. And that evolution can sometimes create the impression of inconsistency. A model that seemed sufficient a decade ago might need revision today. Not because it was wrong, but because it was incomplete. And this brings us to an interesting point of reflection. When we talk about exoplanets, we often speak in terms of discovery. How many have been found? What types they are? How they compare to Earth? But underlying all of that is a more fundamental process: interpretation. We are taking limited signals, tiny dips in starlight, slight shifts in spectral lines, and using them to reconstruct entire worlds. Worlds with atmospheres, temperatures, compositions, and histories. And while the science behind this is rigorous, it still involves layers of inference. We are building models that fit the data, and those models are tested, refined, and sometimes revised as new information becomes available. But they are still models, approximations of reality, not direct observations. And that distinction is important, not because it undermines the science, but because it highlights where the boundaries are. It reminds us that there is a difference between what we know and what we infer. And in that space between knowledge and inference, there is room for careful, grounded curiosity. Because if our current methods are limited, and if our models are shaped by the data we can collect, then there may be aspects of planetary systems that we have not yet fully captured. Not because they are unknowable, but because we are still in the early stages of observing them. And this is where a subtle but meaningful shift in perspective can occur. Instead of viewing exoplanets as a completed catalogue of discoveries, we begin to see them as part of an ongoing process. A process that is still unfolding, still expanding, still refining itself with each new observation. Because every time a new planet is detected, it doesn't just add to the list, it adds to the context. It helps us understand how common certain features are, how systems vary, how different conditions can lead to different outcomes. But it also raises new questions. Questions about what we might be missing. Questions about how our methods influence our conclusions. Questions about how much of the universe remains just beyond our current reach. And as you let your mind follow that idea, gently, without rushing toward an answer, you begin to see that the study of exoplanets is not just about distant worlds. It's about perspective, about how we observe, how we interpret, and how we adjust our understanding as new information becomes available. It's a reminder that knowledge is not fixed. It evolves. And that evolution is not a flaw in the process. It's the process itself. Because in a universe as vast and varied as this one, certainty is not something that arrives all at once. It emerges slowly, gradually, through observation, through analysis, through the willingness to revise what we thought we understood. And exoplanets, in their quiet, distant orbits, are part of that unfolding story, not just as objects of study, but as markers of how far we've come and how much further there is to go. As the search for exoplanets continued to expand, and as detection methods became more refined, a quieter, more subtle question began to take shape. Not just about where planets are or how they form, but about how long they last and what happens to them over time. Because when we look at distant planetary systems, we are not just observing space, we are observing time. The light we receive from these systems has traveled for years, sometimes hundreds or thousands of years, before reaching us. In more distant cases, it has traveled for millions of years. What we are seeing is not the system as it is now, but as it was when that light began its journey. From a mainstream scientific perspective, this is a fundamental aspect of astronomy. Light has a finite speed, and so every observation is, in a sense, a look into the past. This allows astronomers to study not just individual systems, but different stages of stellar and planetary evolution across the galaxy. But when you apply that idea specifically to exoplanets, something interesting begins to emerge. We are not observing a single timeline. We are observing many timelines, all at once. Some of the systems we study are relatively young, still in the early stages of formation, surrounded by disks of gas and dust where planets are still coalescing. Others are mature, stable systems that have existed for billions of years, and still others may be nearing the end of their lifespans as their stars begin to change and expand. So the catalogue of exoplanets is not just a collection of worlds. It is a layered record of planetary evolution. And within that record, there are hints, subtle patterns that suggest how systems change over time. For example, young stars are often surrounded by protoplanetary disks, regions where dust and gas gradually clump together under gravity, forming planetesimals and eventually full-sized planets. This process is relatively well understood in broad terms, supported by both observation and simulation. But the details are still being worked out. Because not all disks evolve the same way. Some appear to dissipate quickly, leaving little time for large planets to form. Others persist longer, allowing more complex systems to develop. The reasons for these differences are not always clear. They could be related to the mass of the star, the composition of the disk, the presence of nearby stars, or even subtle variations in initial conditions. And those initial conditions matter, because once planets begin to form, they start interacting with each other. Their gravitational influences can alter orbits, trigger migrations, or even lead to collisions. Over time, these interactions shape the final structure of the system. From a mainstream perspective, this is a dynamic but understandable process. Given enough time, systems tend to settle into stable configurations. But the path to that stability can be complex, and not all systems reach it. there is growing evidence that many planetary systems may experience periods of instability, phases where orbits shift dramatically, where planets are ejected into interstellar space, or where collisions reshape entire systems. These events are not directly observed in real time, but they are inferred from the structures we see: gaps in debris disks, unusual orbital patterns, the presence of rogue planets, planets that drift through space without orbiting any star, suggest that planetary systems can be far more turbulent than they appear at first glance. And this introduces another layer to the story. Because if planetary systems can change so dramatically over time, then the snapshot we observe today may not reflect the system's past or its future. A system that appears stable now may have undergone significant upheaval in the past. And a system that looks stable today may not remain that way indefinitely. This idea is not speculative in the sense of being unsupported. It is grounded in simulations and supported by indirect evidence. But it is still, in many ways, an evolving area of study, because we are trying to reconstruct long-term processes from limited observations. And that reconstruction is not always straightforward. There are also stars that undergo significant changes over time, expanding into red giants, shedding their outer layers, or collapsing into dense remnants like white dwarfs or neutron stars. These transformations can have profound effects on any surrounding planets. Some planets may be engulfed by their stars. Others may be pushed outward as the star loses mass. Some may survive, orbiting the remnants of their former star in entirely new configurations. From a scientific standpoint, these processes are well understood in terms of stellar evolution, but when applied to planetary systems, they create scenarios that are still being explored. For example, planets have been detected orbiting white dwarfs, stellar remnants that represent the final stages of a star's life. In some cases, the presence of heavy elements in the white dwarf's atmosphere suggests that planetary material has been accreted, possibly from disrupted planets or asteroids. This hints at a kind of long-term evolution that extends far beyond the initial formation of a system. Planets are not just born. They persist, they change, and sometimes they are destroyed. And this brings us to a more reflective point. Because when we think about exoplanets, it's easy to imagine them as static worlds, quietly orbiting their stars in unchanging patterns. But the reality appears to be more dynamic. These systems are shaped by time, by interaction, by processes that unfold over millions or billions of years. And we are observing them at different points along that timeline, which means that every exoplanet we study is not just a place. It is a moment in the life of a system that has a past we are trying to understand, and a future we can only begin to imagine. And as you let that idea settle in, as you picture these distant worlds moving through their orbits, influenced by forces both subtle and immense, evolving slowly over time, you begin to see that the study of exoplanets is not just about space, it's about change. About how systems form, how they adapt, and how they respond to the passage of time. It's about recognizing that even on a cosmic scale, nothing is truly static. Everything is part of a process. And perhaps that's where the deeper curiosity lies. Not just in what these planets are, but in what they have been and what they might become. Because in the end, the universe is not just a collection of objects. It is a sequence of events. And exoplanets are one of the ways we begin to trace that sequence, one system at a time. As the picture of exoplanets becomes more detailed, and as the idea of distant worlds slowly shifts from abstract concept to measurable reality, there is another layer that begins to emerge. One that is less about the planets themselves and more about how we interpret signals that are, by their nature, incredibly faint. Because at the distances we're dealing with, even the most advanced instruments are working at the edge of what is detectable. The signals we receive are often buried in noise, requiring careful filtering, repeated observation, and statistical validation before they are accepted as real. From a mainstream scientific standpoint, this process is rigorous by design. A potential exoplanet signal is not confirmed lightly. It must be observed multiple times, using different methods when possible, and it must fit within well-established physical models. False positives, signals that mimic planetary signatures but are caused by other phenomena, are actively accounted for and ruled out. But even with these safeguards, the process highlights something important. We are not directly observing these worlds. We are interpreting patterns in data. For example, a dip in a star's brightness might indicate a planet passing in front of it. But similar dips can also be caused by stellar activity, star spots, flares, or other variations in brightness. Distinguishing between these possibilities requires detailed analysis, often involving long-term observation and cross-referencing with other data. And even then, there can be ambiguity. Some exoplanet candidates remain in a kind of uncertain category for years, as additional data is gathered to confirm or rule them out. Others are reclassified as new information becomes available. This is not a flaw in the system. It's a reflection of how careful the process is. But it also introduces a subtle point of reflection. Because when you're working with signals this faint, this distant, the line between detection and interpretation becomes very thin. And that thinness invites careful attention. There are also cases where signals appear that don't immediately fit expected patterns. Variations in starlight that are irregular, or changes that don't repeat in a simple, predictable way. In most cases, these are eventually explained through known astrophysical processes, stellar variability, instrumental effects, or complex orbital dynamics. But the fact that such signals appear at all is a reminder of how much complexity exists in these systems. Because stars are not perfectly stable light sources. They are dynamic, active, and sometimes unpredictable. And the instruments we use, while incredibly precise, are not immune to noise or interference. So every detection involves a process of separation, isolating the signal of a planet from the background activity of the star, from the limitations of the instrument, from the randomness inherent in any measurement. And that process, while grounded in solid methodology, is not always straightforward. It requires interpretation, it requires judgment, and it requires a willingness to revise conclusions when new data becomes available. This is especially true when we move beyond detection and into characterization. Because once a planet is confirmed, the next step is to understand it, its size, its mass, its orbit, its atmosphere. And each of these properties is derived from indirect measurements. The size of a planet, for example, is often estimated based on how much light it blocks during a transit. But that measurement depends on the size of the star, which must also be estimated. Any uncertainty in the star's properties carries over into the estimate of the planet. The mass of a planet, derived from radial velocity measurements, depends on the angle of the orbit. If the inclination is not perfectly known, the mass estimate may represent a minimum value rather than an exact one. Atmospheric composition, inferred from spectral analysis, depends on models of how light interacts with gases under different conditions. These models are sophisticated, but they still rely on assumptions. So while the data is real, the picture we build from it is layered. Each layer adds detail, but also introduces potential sources of uncertainty. And this brings us to a broader realization. The study of exoplanets is not just about discovering new worlds. It's about learning how to interpret extremely limited information in a consistent, reliable way. It's about building confidence in conclusions that are based on indirect evidence. And that process, while incredibly advanced, is still evolving. Because as new instruments come online, as new methods are developed, The level of detail we can extract from these distant systems continues to increase. But with that increased detail comes new challenges. More data means more complexity, more variables to account for, more potential for unexpected results. And this is where a more reflective, slightly speculative perspective begins to take shape. Not speculative in the sense of making claims beyond the data, but in the sense of asking how much of the full picture we are actually seeing. Because if our observations are limited, and if our interpretations are built on models that are still being refined, then there may be aspects of these systems that are not yet fully captured. Not because they are hidden in any deliberate way, but because they fall outside the current resolution of our tools. And this idea is not unusual in science. It has happened before. There have been times when observations hinted at something that wasn't fully understood, leading to the development of new theories, new instruments, new ways of thinking. And in many cases, what once seemed unclear eventually became well understood. But the process took time. It required patience, careful analysis, and a willingness to question assumptions. And that same process is happening now in the study of exoplanets. Because each new discovery doesn't just add information, it tests the limits of our current understanding. It challenges us to refine our models, to improve our methods, to look more closely at the data. And as you let that idea settle in, as you imagine the delicate process of extracting meaning from faint signals across vast distances, you begin to see that this field is not just about exploration, it's about interpretation. About how we turn patterns into knowledge, about how we distinguish signal from noise, and about how we remain open to the possibility that what we're seeing is only part of a much larger picture. Because in a universe this vast, with systems this varied, it would be surprising if everything we needed to know was already within reach. More likely, we are still at the edge, looking outward, gathering pieces, and slowly, carefully, learning how they fit together. As we move deeper into the study of exoplanets, there is a quiet shift that begins to take place. A movement from simply identifying planets to asking a more difficult question. What are these worlds actually like beyond their basic measurements? Not just their size or orbit, but their environments, their surfaces, their skies, if they have skies at all. Because once a planet is confirmed, it becomes more than a data point. It becomes a place, at least in theory. And understanding that place requires moving beyond detection into something closer to reconstruction. From a mainstream scientific perspective, this is where atmospheric studies and climate modeling come into play. Using instruments like the James Webb Space Telescope, scientists can analyze the light that filters through a planet's atmosphere during a transit, breaking it down into its component wavelengths to identify chemical signatures. This process, known as spectroscopy, allows for the detection of molecules like water vapor, carbon dioxide, methane, and others. Each of these leaves a distinct imprint on the light spectrum, acting like a kind of chemical fingerprint. But even here, the picture is not complete. Because detecting a molecule is not the same as understanding the full environment. It tells us that a substance is present, but not necessarily how it behaves under the specific conditions of that planet. Temperature, pressure, radiation levels, and atmospheric dynamics all influence how these molecules interact. So when we detect water vapor, for example, we are not necessarily seeing oceans or clouds as we would imagine them on Earth. We are identifying a component that could exist in many different states, depending on the surrounding conditions. And those conditions can vary dramatically. There are exoplanets where temperatures are so high that metals could vaporize, creating atmospheres composed of exotic elements. There are planets where intense radiation might break down molecules as quickly as they form, preventing stable atmospheres from developing. There are worlds where gravity is so strong that it compresses atmospheric layers into dense, unfamiliar structures. From a scientific standpoint, these variations are expected. They arise naturally from the laws of physics applied under different conditions. But when you begin to imagine what these environments might actually be like, not in a fictional sense, but grounded in the data, it becomes clear that many of these worlds would be almost unrecognizable compared to anything in our own solar system. And this leads to an interesting point of reflection. Because when we talk about Earth-like planets, it's easy to assume a certain level of familiarity: blue skies, oceans, continents, weather patterns that resemble our own. But the reality is likely far more diverse. Even small differences in atmospheric composition or stellar radiation could lead to environments that are fundamentally different from Earth, even if the planet falls within the same general category. So the term Earth-like becomes less about similarity and more about approximation, a way of narrowing down possibilities rather than defining them. And this is where climate modeling becomes important. Scientists use complex simulations to estimate how different factors, atmospheric composition, orbital characteristics, stellar radiation, interact to produce specific environmental conditions. These models can suggest whether a planet might have stable temperatures, whether liquid water could persist, whether atmospheric circulation could distribute heat effectively. But like all models, they are based on assumptions. Assumptions about how certain variables interact, how certain processes behave under unfamiliar conditions. And while these assumptions are grounded in known physics, they are still, in some cases, extrapolations. Because we have only one fully understood example of a life-supporting planet. Everything else is, to some degree, a projection. And that projection, while incredibly sophisticated, carries with it a level of uncertainty that is often understated. Not uncertainty in the sense of doubt, but in the sense of openness. An acknowledgement that there may be environmental configurations that we have not yet fully considered. There's also the question of surface conditions. For most exoplanets, we do not have direct images of their surfaces. We infer their characteristics based on density, atmospheric composition, and temperature estimates. A planet with a certain density might be rocky. A certain temperature range might suggest the possibility of liquid water. But these are inferences. We are building a picture from indirect evidence. And while that picture becomes more detailed with each new observation, it is still incomplete. This is where a more reflective line of thought begins to emerge. Because if our understanding of these worlds is built from layers of inference, then there may be aspects of their environments that are not yet fully captured by our models. Not because the models are flawed, but because the data is limited, and that limitation is not a barrier. It's a boundary that continues to expand as our tools improve, but a boundary nonetheless. And within that boundary, there is room for careful curiosity. Because when you consider how many variables are involved in shaping a planetary environment, stellar type, orbital distance, atmospheric composition, geological activity, magnetic fields, it becomes clear that the range of possible outcomes is vast, far more varied than the relatively narrow set of conditions we observe in our own solar system. And that variety suggests something important. That the universe is not just capable of producing Earth-like worlds, it is capable of producing a wide spectrum of environments, some of which may be only partially familiar, and others that are entirely unlike anything we've experienced. And as you let that idea settle in, as you imagine these distant planets with their own climates, their own atmospheric dynamics, their own unique combinations of conditions, you begin to see that the concept of a world is far broader than we once thought, not limited to what we know, but extending into possibilities that are still being explored. And perhaps the most interesting part is that this exploration is not driven by speculation alone. It is grounded in data, measured, analyzed, interpreted, but always with the understanding that interpretation is an ongoing process. that each new observation has the potential to refine the picture or to reveal something unexpected. Because in the end, the study of exoplanet environments is not about confirming what we already believe. It's about discovering what is actually there and learning, step by step, how to understand it. As the understanding of exoplanet environments deepens, another layer begins to emerge, one that sits quietly beneath everything we've discussed so far. It's not about detection or classification or even atmospheric composition. It's about something more subtle, the conditions that allow a planet to remain stable over long periods of time. Because when we look at Earth, one of the most important factors is not just that it exists in a habitable zone, or that it has the right composition, but that these conditions have remained relatively stable for billions of years. Long enough for complex processes to unfold gradually. And when we begin to apply that idea to exoplanets, the question becomes more complex. It's not just about whether a planet could support certain conditions. It's about whether those conditions can persist. From a mainstream scientific perspective, planetary stability depends on a combination of factors. The orbit must remain relatively consistent, avoiding extreme variations in distance from the star. The star itself must be stable enough, not producing excessive radiation that could disrupt the planet's atmosphere. The planet may also benefit from a magnetic field, which can protect its surface from stellar winds and cosmic radiation. On Earth, for example, the magnetic field plays a significant role in shielding the atmosphere. Without it, solar wind could gradually strip away atmospheric particles, as is believed to have happened on Mars. Mars shows evidence of having once had a thicker atmosphere and possibly liquid water on its surface. But over time, much of that atmosphere was lost. From a scientific standpoint, this provides a useful comparison, because it demonstrates that habitability is not just about location, it's about retention. A planet might begin with favorable conditions, but if it cannot maintain them, those conditions may not last. And this brings us back to exoplanets. When we detect a planet in the habitable zone, we are identifying a potential. But we are not necessarily seeing a stable, long-term environment. That stability depends on factors that are often difficult to measure from a distance. For example, orbital dynamics. Some exoplanets exist in systems where gravitational interactions with other planets could lead to changes in their orbits over time. Even small variations could shift a planet in and out of the habitable zone, altering its climate in ways that might prevent long-term stability. From a modeling perspective, these interactions can be simulated, and in many cases, systems appear stable over long timescales. But these simulations rely on current observations, and even small uncertainties in initial conditions can lead to different outcomes over millions of years. So again, we are working with probabilities rather than certainties. There's also the question of stellar evolution. Stars change over time. As they age, their brightness can increase, gradually shifting the habitable zone outward. A planet that is comfortably within that zone at one point in time might find itself too hot or too cold at another. In our own solar system, the Sun has gradually increased in luminosity over billions of years. Earth's climate has remained relatively stable despite this, due in part to feedback mechanisms in the atmosphere and geological processes like the carbon cycle. But whether similar stabilizing mechanisms exist on other planets is still unknown. And that uncertainty becomes more noticeable when we consider planets around different types of stars. Red dwarf stars, for example, can remain stable for extremely long periods, far longer than stars like our Sun. But they also tend to have more intense early activity, with frequent flares that could impact planetary atmospheres. So a planet orbiting a red dwarf might face a different kind of challenge, not long-term stellar instability, but early environmental stress that could shape its development. From a mainstream perspective, these factors are part of ongoing research. scientists are actively studying how different types of stars influence planetary environments over time. But from a broader point of view, it highlights something important. That stability is not guaranteed. It is the result of multiple factors aligning over long periods. And this alignment may be more delicate than it appears. Because when you consider how many variables are involved, orbital mechanics, stellar behavior, atmospheric chemistry, magnetic fields, it becomes clear that maintaining stable conditions is not just about being in the right place. It's about maintaining the right balance. And that balance can be influenced by events that are, in many cases, unpredictable. Asteroid impacts, for example, can alter a planet's climate significantly. Volcanic activity can change atmospheric composition. Gravitational interactions can shift orbits. These are not hypothetical scenarios. They are processes that have occurred in our own solar system, and they remind us that planetary environments are dynamic. They change over time, sometimes gradually, sometimes abruptly. And this leads to a more reflective line of thought. Because when we look at exoplanets and ask whether they might support life, we are often focusing on a snapshot, what the conditions might be like now. But life, especially complex life, requires time. It requires stability over long periods. And that stability may be one of the more challenging aspects to assess from a distance. Not because it's unknowable, but because it involves processes that unfold over timescales far beyond our observations. We are seeing moments, not entire histories. And those moments, while informative, may not capture the full picture. So when we consider the possibility of Earth-like conditions elsewhere, it's worth asking not just where those conditions exist, but how long they last. Because a planet that briefly passes through a habitable phase might be very different from one that maintains those conditions for billions of years. And that distinction, while subtle, could be significant. It shifts the focus from possibility to persistence, from potential to duration. And as you let that idea settle in, as you imagine these distant worlds, not just as places, but as systems evolving over time, balancing variables, responding to changes, maintaining or losing stability, you begin to see that habitability is not a fixed state. It is a process. One that unfolds gradually, shaped by a combination of factors that must align and continue to align over long periods. And that process, quiet and complex, may be one of the most important aspects of understanding exoplanets. Not just whether they can support certain conditions, but whether they can hold on to them. Because in the end, the difference between a world that briefly resembles Earth and one that remains stable long enough for something more to develop may come down to time, and time, in the context of the universe, is both abundant and unevenly distributed. As the discussion around exoplanets continues to deepen, and as more attention is given to stability, time, and environmental balance, another question begins to emerge. One that sits quietly beneath all the others, but carries a certain weight when you stop to consider it. Not just where planets are, or what they are like, but how often the conditions we associate with complexity actually come together in one place. Because up to this point, we've been working with layers of possibility. A planet exists. It orbits within a certain range. It may have an atmosphere. It may retain heat. It may remain stable over long periods. Each of these is a condition, and each condition on its own is not especially rare. But when you begin to combine them, the picture becomes more selective. From a mainstream scientific perspective, this is often framed in terms of probability. Not a single defining factor, but a series of overlapping requirements. The right distance from the star, the right planetary mass, the presence of an atmosphere, long-term orbital stability, a relatively stable star, perhaps a magnetic field, perhaps geological activity that helps regulate atmospheric composition. None of these are impossible. In fact, many of them appear to be relatively common, when considered individually. But together, they begin to form a narrower window. And this is where the conversation becomes more nuanced, because it's not just about whether Earth-like conditions exist elsewhere. It's about how frequently they persist in a way that allows complexity to develop over time. From one perspective, the sheer number of stars in the galaxy, hundreds of billions, suggests that even rare combinations of conditions could occur many times. Even if only a small fraction of stars host planets with the right characteristics, that fraction applied across such a large number still results in a significant number of potential candidates. This is often the basis for the idea that Earth-like worlds may not be unique. But from another perspective, the specific alignment of conditions required for long-term stability might be less common than the individual factors suggest. Small variations in any one parameter could shift the balance, leading to environments that are either too unstable, too extreme, or too short-lived for complex processes to unfold. And both of these perspectives are grounded in the same data. They differ not in the facts themselves, but in how those facts are interpreted, because the data tells us how many planets there are, what sizes they tend to be, how they orbit their stars. But it does not yet tell us how often all the necessary conditions align in the same place, over the same period of time. And this is where a more reflective line of thought begins to take shape. Because when you step back and look at the broader picture, you begin to see that the question is not just about abundance or rarity, it's about distribution. How are these conditions spread across the galaxy? Are they clustered in certain types of systems? Are they evenly distributed, or do they depend on specific environments? For example, stars in densely populated regions of the galaxy may experience more gravitational interactions, potentially disrupting planetary systems. Stars in more isolated regions might have more stable environments, but fewer interactions that could influence planetary formation. Even the composition of the interstellar medium, the gas and dust from which stars and planets form, can vary from one region to another, affecting the types of planets that emerge. From a scientific standpoint, these factors are part of ongoing research. Astronomers are studying how galactic environments influence star and planet formation, looking for patterns that might help explain the distribution of different types of systems. But the picture is still incomplete, because the galaxy is vast, and our observations, while expanding, still cover only a small fraction of it. And that incompleteness leaves room for careful consideration. Not for conclusions, but for questions. Because if the conditions for long-term stability and complexity are influenced by multiple layers, stellar type, planetary characteristics, system dynamics, galactic environment, then the likelihood of those conditions aligning may depend on more than just local factors. It may depend on context. And context is something we are only beginning to understand on a galactic scale. There's also another aspect to consider, one that is often less discussed but quietly significant: time. Not just the stability of individual planets, but the timing of when those planets form relative to their stars and their environments. A planet that forms early in a system's history may experience different conditions than one that forms later. A star that forms in a region rich in heavy elements may produce different types of planets than one that forms in a more primordial environment. Even the age of the galaxy itself plays a role. Early in the galaxy's history, there were fewer heavy elements available, which are necessary for forming rocky planets. Over time, as generations of stars lived and died, these elements became more abundant, increasing the likelihood of Earth-like planets forming. So the distribution of potentially habitable worlds may not just be a matter of space, but of time as well. And this adds another layer to the question, because it suggests that the conditions we're looking for may not be evenly distributed across the history of the galaxy. They may be more common in certain eras, less common in others, and we happen to exist at a particular point along that timeline. From a mainstream perspective, this idea is part of broader studies in galactic evolution. It's not speculative in the sense of being unsupported, but it is still being explored, still being refined. And from a broader perspective, it highlights something that is easy to overlook: that our observations are not just limited by distance, but by when we are observing. We are looking out into space, but also back in time, sampling different moments across the galaxy's history, and trying to piece them together into a coherent picture. And as you let that idea settle in, as you imagine the galaxy not just as a static collection of stars, but as a dynamic system evolving over billions of years, with conditions changing, environments shifting, possibilities emerging and fading, you begin to see that the question of how common Earth-like worlds are is not a simple one. It's layered, dependent on multiple factors, interacting across both space and time. And perhaps that's what makes it so compelling. Not that there is a single answer waiting to be found, but that the process of searching for that answer reveals more about the structure of the universe itself. Because in trying to understand how often the right conditions come together, we are also learning how those conditions are created, how they are maintained, and how they change. And that understanding, gradual and evolving, becomes part of a much larger picture, one that extends beyond individual planets, into the deeper patterns that shape the galaxy as a whole. As the search for exoplanets continues to expand, and as the questions become more refined, there is another layer that begins to emerge, one that is less about physical measurements and more about interpretation at the edge of uncertainty. Because as we've seen, much of what we know about these distant worlds comes from indirect signals, carefully analyzed and cross-checked against models that are themselves evolving. And while this process is grounded in rigorous science, it occasionally produces results that are not immediately clear, not incorrect, not unexplainable, but not instantly intuitive either. There have been cases where observed data initially suggested something unusual, light curves that didn't follow expected patterns, variations in brightness that seemed irregular, or signals that changed over time in ways that required additional analysis to understand. From a mainstream perspective, these anomalies are part of the process. They are investigated, compared against known phenomena, and often resolved through more detailed observation. Stellar activity, instrumental noise, dust clouds, or complex orbital dynamics can all produce signals that mimic or obscure planetary signatures. And over time, most of these anomalies are explained within the existing framework. But the fact that they appear at all is worth noting, because it highlights how complex these systems can be and how careful we need to be when interpreting limited data. One of the more widely discussed examples of this kind of observation involves KIC 8462852, sometimes referred to as Tabby's star. This star exhibited irregular and significant dips in brightness that did not match the typical patterns associated with orbiting planets. From a scientific standpoint, several natural explanations have been proposed: clouds of dust, cometary fragments, or other forms of circumstellar material that could intermittently block the star's light. And over time, evidence has increasingly supported these more conventional explanations. But what made this case particularly interesting was not the final conclusion. It was the process. Because for a period of time, the data did not fit neatly into existing models. It required new observations, new hypotheses, and careful analysis to understand what was happening. And that process is a reminder of something important: that science does not always move in straight lines. It moves through questions, through observations that lead to further investigation, through patterns that require interpretation, through moments where the data is clear, but the meaning is still being worked out. And in the study of exoplanets, where the signals are faint and the distance is immense, this kind of process is not unusual. It's expected. because we are operating at the limits of what can be observed. And at those limits, there will always be moments where the data challenges our expectations. Not in a dramatic or mysterious way, but in a quiet, technical sense, where something doesn't quite fit and requires a closer look. And this is where a more reflective perspective begins to take shape. Because when you consider how much of our understanding is built on interpretation, on translating signals into models, on fitting observations into frameworks, it becomes clear that there is a balance between confidence and caution. Confidence in the methods, in the data, in the consistency of the results, and caution in how those results are interpreted, especially when they push against the edges of what we currently understand. This balance is not always visible from the outside. Scientific findings are often presented in clear terms, with conclusions that reflect the best available understanding. But behind those conclusions is a process that involves uncertainty, revision, and ongoing refinement. And that process is particularly important in a field like this. Because exoplanets are not directly accessible, we cannot visit them, cannot sample their surfaces, cannot observe them up close. We rely entirely on distant measurements, and while those measurements are incredibly precise, they are still limited. So when we encounter something unusual, something that doesn't immediately fit, it becomes an opportunity, not to jump to conclusions, but to ask better questions, to refine our models, to improve our instruments, to gather more data. And over time, those questions often lead to deeper understanding, but not always immediately. Sometimes the answer takes years to emerge. Sometimes it requires new technology. Sometimes it changes the way we think about the system entirely. And this is where the study of exoplanets becomes more than just a catalogue of discoveries. It becomes a process of exploration in the truest sense. Not just finding new worlds, but learning how to understand them. Learning how to interpret signals that are subtle, complex, and sometimes ambiguous. And as you let that idea settle in, as you imagine the quiet process of observation, analysis, revision, repeated over and over again, across different systems, across different distances, you begin to see that this field is not defined by certainty, it's defined by progress, by the gradual refinement of understanding, by the willingness to follow the data, even when it leads somewhere unexpected. And perhaps that's where the deeper sense of curiosity comes from. Not from the idea that there are unknowns, but from the realization that those unknowns are being approached carefully, methodically, with tools that continue to improve. Because in the end, the study of exoplanets is not about reaching a final answer. It's about continuing to ask questions that bring us closer to understanding what's actually out there, and recognizing that each answer is part of a larger process, one that is still unfolding. As the field of exoplanet research continues to mature, and as the accumulation of data begins to form not just isolated discoveries, but a broader, interconnected picture, there is a gradual shift in focus, one that moves from identifying individual systems to recognizing patterns across many of them. Because when you have only a handful of examples, each one feels unique. But when the number grows into the thousands, patterns begin to emerge. Not always obvious at first, but slowly becoming clearer as more data fills in the gaps. And these patterns are not always what we expected. From a mainstream scientific perspective, one of the most notable trends is the apparent abundance of compact planetary systems. Systems where multiple planets orbit very close to their star, often in tightly spaced, orderly arrangements. These systems appear to be relatively common, especially around smaller stars. This stands in contrast to our own solar system, where the planets are more widely spaced, with significant gaps between their orbits. At first glance, both configurations are consistent with planetary formation models. Variations in the protoplanetary disk, the distribution of material, and the timing of formation can lead to different outcomes. But when one configuration appears more frequently than another, it invites a deeper look. Why do compact systems seem so common? What conditions favor their formation? And why does our own system not follow that same pattern? These are not contradictions, but they are areas where our understanding is still being refined. Because while models can reproduce compact systems under certain conditions, they often require specific initial parameters, particular distributions of mass, specific rates of migration, certain interactions between forming planets. And while those parameters are plausible, the frequency with which these systems appear suggests that the underlying processes may be more flexible than we once thought. There's also the matter of orbital resonance, which we touched on earlier, but becomes more significant when viewed across multiple systems. In many compact systems, planets are found in resonant chains, where their orbital periods are related by simple ratios, 2:1, 3:2, and so on. This creates a kind of gravitational rhythm, where the planets influence each other in regular, predictable ways that contribute to the system's stability. From a scientific standpoint, these resonances can form naturally during planetary migration. As planets move through the protoplanetary disk, they can become locked into these ratios, maintaining them over long periods. But again, the consistency of this pattern across different systems raises questions about how common these migration processes are, and how often they lead to stable, resonant configurations. Because while the physics allows for it, the repetition of the pattern suggests it may be more than just an occasional outcome. It may be a common pathway. And this idea of common pathways begins to shift the way we think about planetary systems. Instead of viewing each system as a unique result of random processes, we begin to see that there may be preferred outcomes, shaped by the underlying physics in ways that we are still trying to fully understand. Not deterministic in a strict sense, but guided, influenced by factors that tend to produce certain structures more often than others. And this brings us to another pattern that has started to emerge: the apparent scarcity of certain types of planets in specific regions. For example, there appears to be a relative lack of planets of certain sizes within very close orbits around their stars, a phenomenon sometimes referred to as a radius gap. Planets tend to cluster either below or above a certain size range, with fewer in between. From a mainstream perspective, this can be explained by atmospheric loss. Smaller planets may lose their atmospheres due to intense stellar radiation, leaving behind dense rocky cores. Larger planets, with stronger gravity, are better able to retain their atmospheres. Over time, this process could create a gap in the observed distribution. But like many patterns in exoplanet data, this explanation, while plausible, is still being studied. It depends on models of atmospheric escape, stellar activity, and planetary composition, all of which involve variables that are not always directly observable. So once again, we find ourselves in a position where the data suggests a pattern, and the explanation is being refined. And this is where a more reflective perspective begins to take shape. Because when you step back and look at these patterns, compact systems, resonant orbits, size distributions, you begin to see that the universe is not just producing planets at random. It is producing them within a framework, a set of underlying rules that guide how matter organizes itself under the influence of gravity, motion, and time. But those rules, while consistent, allow for a wide range of outcomes, and that range is what we are beginning to map. Not completely, not with perfect clarity, but gradually. And as that map becomes more detailed, it starts to reveal not just individual systems, but relationships between them. Connections that were not visible when the data was sparse. And this is where the study of exoplanets begins to resemble something more like pattern recognition. Looking for regularities, for trends, for deviations that might point to new insights. Because sometimes the most important discoveries are not the ones that stand out, but the ones that repeat, the ones that appear again and again, quietly suggesting that there is something fundamental at work. And as you let that idea settle in, as you imagine these distant systems forming, evolving, arranging themselves into patterns that reflect deeper processes, you begin to see that the study of exoplanets is not just about expanding our knowledge of distant worlds. It's about understanding the principles that shape all planetary systems, including our own. Because by comparing what we see elsewhere with what we observe here, we gain perspective. We begin to see what is common, what is unusual, what might be typical, and what might be an exception. And that perspective is valuable because it helps us place our own solar system within a larger context, not as the standard by which all others are measured, but as one example among many. And perhaps that shift, from assuming we are typical to exploring how we fit into a much broader range of possibilities, is one of the more subtle but meaningful changes that exoplanet research has brought about. Because it encourages a different kind of thinking, one that is less about certainty and more about understanding variation, about recognizing patterns, but also paying attention to the exceptions. Because in those patterns and exceptions, there is information, clues about how the universe works on scales far beyond our immediate experience. And those clues, gathered slowly over time, begin to form a picture. Not a final picture, not a complete one, but one that is becoming clearer with each new observation. As the broader patterns of exoplanet systems begin to settle into something more recognizable, there is a quieter question that starts to take shape. Not about how planets form or how they are distributed, but about how they are detected in relation to something even more subtle, the limits of our own perspective. Because everything we've discussed so far, every planet, every system, every pattern, has been observed from a single vantage point, Earth. Every signal we interpret, every dip in brightness, every spectral line, every inferred atmosphere, all of it is filtered through our position in space, our line of sight, and the tools we've built to extend that view. From a mainstream scientific standpoint, this is simply the reality of observation. We observe the universe from where we are, and while that might seem obvious, the implications of it are often more complex than they first appear. Because our position introduces a kind of observational bias that is not always immediately visible. For example, the transit method, which has been responsible for a large portion of exoplanet discoveries, depends entirely on alignment. If a planetary system is oriented in such a way that its planets do not pass directly between their star and Earth, then those planets will not produce the characteristic dip in brightness that we rely on for detection. So entire systems may exist, completely undetected, simply because of their orientation relative to us. And this is not a small effect. Statistically, only a fraction of planetary systems will be aligned in a way that allows transits to be observed from Earth. The rest remain invisible to this method. From a scientific perspective, this is accounted for in population estimates. Astronomers use statistical models to infer the likely number of unseen planets based on the ones we do detect. But even with those corrections, there is an underlying limitation, because we are still working from a single viewpoint. We are not observing these systems from multiple angles. We are not seeing their full three-dimensional structure in real time. We are reconstructing it. And that reconstruction depends on how the system appears from our specific position. There's also the matter of distance. Closer systems can be observed in greater detail. Their signals are stronger, their characteristics easier to measure. More distant systems, while still detectable in some cases, provide less detailed information. So our catalogue of exoplanets is not just shaped by what exists, but by what is close enough, bright enough, and aligned in a way that allows us to detect it. This creates a kind of observational landscape, where certain types of systems are more visible than others. And while this is well understood within the scientific community, it adds another layer to how we interpret the data. Because when we see patterns, when we notice that certain types of planets appear more common, we have to ask, are these patterns intrinsic to the universe? Or are they influenced by the way we are observing it? And the answer is often both. Some patterns are real, reflecting underlying physical processes that shape planetary systems. Others are amplified, or even created, by the limitations of our detection methods. And distinguishing between the two requires careful analysis. It requires comparing different detection techniques, looking for consistency across methods, and accounting for biases in the data. But even with that effort, there is still a boundary, a point beyond which our current observations cannot reach. And this is where a more reflective perspective begins to emerge. Because when you consider how much of our understanding is shaped by our position, by where we are, how we observe, what we are able to detect, it becomes clear that there may be aspects of the universe that are simply outside our current field of view, not hidden in any intentional sense, just beyond our observational horizon. And this idea is not unusual in science. There have always been limits to what we can observe directly, and those limits have gradually expanded as technology improves. But at any given moment, there is always a boundary. And beyond that boundary, there is more. More systems, more planets, more variations that we have not yet seen. And perhaps more importantly, more context. Because our understanding of exoplanets is not just about the planets themselves. It's about how those planets fit into a larger framework. A framework that includes not just individual systems, but the relationships between them, the distribution across the galaxy, the influence of different environments. And that framework is still being built, piece by piece, observation by observation. And as you let that idea settle in, as you imagine the vast number of systems that may exist beyond what we can currently detect, quietly orbiting their stars, following paths we have not yet mapped, you begin to see that the study of exoplanets is not just about what we have found, it's about what we are still learning how to see. Because every improvement in our ability to observe, every new telescope, every new method, doesn't just add detail, it expands the boundary. It brings more of the universe into view. And with that expansion comes a shift in perspective. Because what once seemed rare may turn out to be common. What once seemed common may turn out to be a product of how we were looking. And this constant adjustment, this ongoing refinement of perspective, is part of what makes this field so dynamic. Not fixed, not final, but evolving. And perhaps that's the most important thing to take away, that our understanding of exoplanets is not just a collection of facts. It is a process shaped by observation, by interpretation, by the gradual expansion of what we are able to detect and understand. And within that process, there is always more to explore, more to question, more to discover. Because the universe, in all its complexity, is not limited by our current perspective. It extends far beyond it, and we are only beginning to see how much further it goes. As we continue to follow this expanding picture of exoplanets, their patterns, their variations, and the limits of how we observe them, there is one final layer that begins to come into focus. A layer that is less about the planets themselves and more about what their existence quietly implies. Because when you step back from the details, the measurements, the models, the classifications, you begin to notice something that is easy to overlook. Planets are not rare, not in the sense we once imagined. There was a time, not long ago, when the existence of planets beyond our solar system was still uncertain. Now, not only do we know they exist, but we know they are widespread, common, a natural outcome of star formation. From a mainstream scientific perspective, This is one of the most significant discoveries of the last few decades. It suggests that wherever stars form, planets are likely to form as well. The processes that create them, gravity pulling together gas and dust, forming disks, building structures over time, are not unusual. They are part of the standard behavior of matter under the conditions present in the universe. And this realization shifts the foundation of the question. Because if planets are common, then the environments we've been discussing, the variations, the extremes, the stable systems, the unstable ones, are not isolated cases. They are part of a larger pattern, a pattern that extends across the galaxy. And when you consider that, another question naturally follows. Not just how many planets exist, but how many different kinds of environments those planets represent. Because each planetary system is shaped by its own history, its star, its formation process, its interactions over time. And as we've seen, even small differences in those factors can lead to very different outcomes. So the number of distinct environments, the number of ways a planet can exist, evolve, and stabilize may be far greater than we initially assumed. From a scientific standpoint, this diversity is expected. It arises from the same physical laws applied under different initial conditions. But when you take a moment to consider the scale of it, it becomes something more than just a technical detail. It becomes a perspective, because it suggests that the universe is not just populated, it is varied, deeply varied. And that variation is not random, but structured, guided by underlying processes that produce both patterns and exceptions. And this brings us back, in a quiet way, to the question that has been present throughout this exploration. Not stated directly, but always there in the background. What does all of this mean for how we understand our place in the universe? From a mainstream perspective, the answer is still developing. The discovery of exoplanets has expanded our understanding, but it has not yet provided definitive answers to the deeper questions about life, rarity, or uniqueness. It has, however, changed the context in which those questions are asked. Because we are no longer asking whether other worlds exist. We are asking what those worlds are like, and how often conditions similar to ours might occur, and whether those conditions, when they do occur, follow similar paths, or entirely different ones. But from a broader, more reflective point of view, there is another layer to consider. Because the existence of so many planets, in so many configurations, suggests that the processes that shape them are both robust and flexible. Capable of producing stability, but also capable of producing extremes, capable of creating environments that persist and others that change rapidly. And within that range, somewhere, are the conditions we recognize, not necessarily unique, not necessarily common, but part of a spectrum. And that idea, that what we experience here is one point within a much larger range of possibilities, carries a certain quiet significance. Not because it answers the question of how common Earth-like worlds are, but because it reframes the question itself. It shifts the focus from comparison to context, from asking whether we are typical, to understanding how we fit into a much broader system. And that shift is subtle, but meaningful, because it encourages a different way of thinking. One that is less centered on finding exact matches, and more focused on understanding variation, on recognizing that similarity can exist in degrees, not just in absolutes. And as you let that idea settle in, as you imagine the countless worlds that exist beyond our view, each one shaped by its own conditions, its own timeline, its own interactions, you begin to see that the study of exoplanets is not just about distant places. It's about expanding perspective, about moving beyond the assumption that what we know is the standard, and beginning to explore how much variation can exist within the same set of underlying rules. Because in the end, the universe does not appear to be built around a single template. It appears to be built around possibilities. And those possibilities, while grounded in consistent physical laws, are expressed in ways that are still being discovered, still being mapped, still being understood. And perhaps that is where the deeper sense of curiosity comes from. Not from the idea that there are answers waiting to be found, but from the realization that the process of finding them reveals something larger. Something about how systems form, how they evolve, and how they fit together across vast distances and timescales. Because exoplanets, in their quiet, distant orbits, are not just objects of study. They are part of a pattern that we are only beginning to see. And as that pattern becomes clearer, it doesn't close the question, it opens it further, inviting us to look deeper, to ask more carefully, and to continue exploring, one observation at a time. And as we begin to approach the outer edges of this exploration, where the accumulation of observations, patterns, and careful interpretations starts to settle into something more reflective, there is one final direction the mind naturally drifts toward. Not outward this time, but inward. Because after considering thousands of distant worlds, after tracing how they form, how they evolve, how they vary across space and time, there is an almost inevitable shift in perspective. We begin to look back, not in a dramatic way, not with conclusions, but with a quieter kind of comparison. Because everything we've discussed, orbital stability, atmospheric balance, stellar influence, long-term persistence, these are not abstract ideas. They are the same factors that shape our own planet. And when viewed through the lens of exoplanets, those familiar conditions begin to look slightly different. From a mainstream scientific standpoint, Earth is understood as the result of natural processes, shaped over billions of years through interactions between geology, atmosphere, and solar input. Its position in the habitable zone, its relatively stable orbit, its magnetic field, its active geology, all of these contribute to the environment we experience. There is nothing in this explanation that falls outside established physics. But when you place Earth within the broader context of exoplanet data, something subtle begins to stand out. Not as an anomaly, but as a configuration. A particular arrangement of factors that, while not necessarily unique, is clearly specific. Because as we've seen, many planets exist in the habitable zone, but may lack stable atmospheres. Others may have thick atmospheres, but orbit volatile stars. Some may have the right composition, but experience orbital instability over time. Earth appears to sit at a kind of intersection, where multiple variables align in a way that allows long-term stability. And again, from a scientific perspective, this can be understood as the result of initial conditions and subsequent evolution. The solar system formed in a way that led to this outcome. The processes involved are consistent with what we observe elsewhere, but the alignment itself remains something worth considering, not as a mystery, but as a point of perspective. Because when you step back and look at the range of planetary systems we've discussed, the diversity, the extremes, the variations, you begin to see that stable, long-term environments may represent a narrower subset within that range. Not vanishingly rare, but not guaranteed either. And this brings us to a more reflective question. Not whether Earth is unique, but how often similar configurations persist long enough, under stable enough conditions, to allow complexity to develop. And this is where the conversation naturally slows, because this is not a question with a clear answer. Not yet. From a mainstream standpoint, research continues. More exoplanets are being studied. More data is being collected. Models are being refined. Over time, the statistical picture will become clearer. But for now, we are still in the early stages. We are identifying candidates, analyzing atmospheres, studying orbital dynamics. We are building a data set, and that data set, while already extensive, is still incomplete. So instead of conclusions, what we have are indications. Signals that suggest certain patterns, certain probabilities, certain ranges of possibility, but not definitive answers. And perhaps that's where the most grounded perspective lies. Not in assuming rarity and not in assuming abundance, but in recognizing that the question itself is still open. Because the universe, as we are beginning to understand it, does not seem to operate in simple binaries. Things are not simply common or rare. They exist along spectrums, influenced by multiple factors, interacting over time. And Earth, within that framework, is one example. A detailed, well-understood example, but still just one. And as you let that idea settle in, as you imagine the countless other worlds that exist beyond our view, each one shaped by its own conditions, its own history, its own balance of variables, you begin to feel a shift in how the question is framed. It becomes less about comparison and more about context. Less about asking whether other worlds are exactly like ours, and more about understanding how many different ways a world can exist. Because in the end, the study of exoplanets is not just about finding another Earth. It's about expanding the definition of what a world can be, and recognizing that within that expanded definition, there may be forms of stability, forms of complexity, forms of persistence that we have not yet fully considered, not because they are beyond understanding, but because we are still learning how to look. And that process, slow, careful, grounded in observation, is what continues to move this field forward, not toward a final answer, but toward a clearer picture, one that becomes more detailed with each new discovery, more refined with each new model, more complete with each new perspective, and yet still open, still evolving, still inviting further exploration. Because the universe, in all its scale and variation, does not close its questions easily. It allows them to unfold, gradually, over time. And as you follow that unfolding, letting the ideas settle without needing resolution, you begin to see that perhaps the most important part of this exploration is not the answers themselves, but the way the questions continue to expand. And now, as everything we've explored begins to settle into a quieter, more reflective view, the focus naturally shifts, not toward a final answer, but toward the shape of the journey itself. Because when you trace the path we've taken, from the first confirmed detections of exoplanets to the thousands now catalogued, from simple measurements of starlight to detailed atmospheric analysis, from isolated discoveries to emerging patterns, what becomes clear is not just what we've found, but how we've learned to find it. And that process is still unfolding. From a mainstream scientific perspective, the study of exoplanets is one of the fastest evolving fields in modern astronomy. New instruments are being developed, new missions planned, each one designed to extend the limits of what we can observe. Telescopes are becoming more sensitive, capable of detecting smaller planets, analyzing thinner atmospheres, resolving finer details. But even with all of that progress, there is a recognition, quiet but consistent, that we are still at the beginning. Because every improvement in our ability to observe does not simplify the picture. It adds to it. It reveals new layers of complexity, new variations, new exceptions to patterns we thought we understood. And that is not a setback. It is a sign that we are moving closer to a more complete understanding. Because the universe, as it presents itself through exoplanets, does not appear to be built around uniformity. It appears to be built around variation within structure. The same physical laws applied across different conditions, producing outcomes that are both predictable in principle and diverse in detail. And that balance between consistency and variation is what makes the study of these distant worlds so compelling. Because it means that every new discovery has the potential to both confirm what we expect and expand what we consider possible. And as you let that idea settle in, as the details of planets, systems, atmospheres, and timelines begin to fade into a broader perspective, something else becomes clear. That this exploration is not just about distant places, it is about perspective itself. Because for most of human history, the night sky was a surface, a backdrop, a pattern of lights whose deeper nature was unknown. Then, gradually, it became something more. Stars, galaxies, structures extending far beyond what we could see. And now, it has become something even more detailed. Not just stars, but systems. Not just systems, but worlds. Worlds that orbit, evolve, interact, persist, and change. And this shift, from seeing points of light to understanding them as places, changes how we relate to the universe. Not in a dramatic or emotional way, but in a subtle expansion of context. Because it means that when you look at the night sky, you are not just seeing distant stars. You are seeing the centers of systems. Systems that may contain planets. Planets that may have atmospheres, climates, histories. And even if we cannot see those details directly, we know they are there, measured, inferred, understood within the limits of our current knowledge. And those limits continue to expand. Because the tools we use will improve. The data will grow. The models will be refined. And with each step, the picture will become clearer. Not complete, but clearer. And perhaps that is the most grounded way to understand where we are. Not at the end of discovery, but in the early stages of a much longer process. A process that is not driven by certainty, but by curiosity guided by evidence. Because in the end, the study of exoplanets is not about proving a single idea. It is about exploring a range of possibilities, constrained by observation, shaped by data, refined over time. And within that exploration, there is a kind of quiet consistency, a method. Observe carefully, interpret cautiously, adjust when necessary, and continue. And as everything begins to settle, as the questions remain open but more clearly defined, as the patterns become visible but not fully explained, there is a final thought that lingers. Not as a conclusion, but as a perspective. That the universe is not just larger than we once thought, it is more varied, more flexible in its outcomes, more open in its possibilities, and that within that vast range, our own world is one example, not the center, not the template, but a point within a much broader spectrum. And understanding that spectrum is what this entire exploration has been about, not reaching an endpoint, but expanding the frame, so that when we look outward, we are not just searching for something familiar. We are learning how to recognize what is actually there. And that process, slow and ongoing, is what continues to carry this field forward. One observation at a time, one question at a time, one world at a time. And somewhere out there, beyond the limits of what we can currently detect, beyond the faint signals and distant light, there are still more worlds, waiting to be understood, not hidden, just not yet seen. And that is where the story remains, open.